In this video, I'm going to discuss molecular shapes and how they're related to the different bond types. So let's talk about molecules that contain all single bonds. And we're going to look at two different things. We're going to look at both the electron pair geometry and we're also going to consider the molecular shape. So if, for example, we had a molecule that was just one atom in the middle, let's call it A, is in the middle, atom A is in the middle, and it's single bonded to element B. Now, in this particular case, we're going to have three sets of unshared pairs around that. So we have an unshared pair, and unshared pair. When we have that situation, our electron pair geometry would be tetrahedral. So when you have four pairs of electrons coming out from that central atom like this, the electron pair geometry is automatically going to be tetrahedral. Now, when you only have the 1B atom here attached to our A atom, then the molecule will be linear in configuration because you only have two atoms. And so when we consider the electron pair geometry, it's just what it means. The electron pairs, we're looking at the electron pairs. So here we have one pair, another pair down here, a pair coming out at us, and that fourth pair going off to the top here. So those four pairs of electrons here, I'll just pull off that other atom, those four pairs of electrons then are going to form a tetrahedral configuration. Now, if we were to consider just the four pairs of electrons here and the endpoints of these four pairs of electrons that are coming out from the central atom, it would form a tetrahedral configuration. And when we're considering the molecular shape, we consider just the atoms themselves, okay? So here we only have the two atoms, and as a consequence, you're just going to have a linear molecule because you only have two atoms. But now what if we added another B atom to this? So I'm going to remove this pair of electrons here and make it a bond to another B atom. Now, the electron pair geometry still remains the same because we have four pairs of electrons coming out from that central atom, okay? So it's still going to be a tetrahedral configuration, but now with two atoms coming out from that central central atom, then our configuration is going to be bent. We can see that from here. Okay, so now we build our molecule, and really, no matter where I put that second atom, no matter which end I attach it to, it's always going to end up being in a bent configuration, no matter where you put it. So I could move it to any one of those other electron pairs, and my configuration will always be bent as such. If we were to add yet a third B atom, so we remove yet another one, another pair, and put in a bond here, and we add a third B atom to this. This one, okay, because we add that third, now we've got two, again, that we're going to have three atoms here. Two of the B atoms are in one plane, and then there's one atom that's going to come out at us. So again, going with that three-dimensional effect, putting it at the edge of our desk, building the molecule and putting it on the edge of our desk so that we can see how it would lie on the plane. And so it looks something of this nature, whereby two atoms are in one plane here, and two B atoms are in one plane, and then that third B atom is coming out at us right now, okay? So when we draw that one, obviously we either draw, in this case, the way I've done it is it's going to come out at us, so I draw it as a triangle. And now when we have that third B atom in there, the molecular shape for this is going to be trigonal pyramid. You can see that the molecule forms somewhat of a pyramid. But now when we think of a pyramid like the pyramids in Egypt, their base is square. And in this case, the base is going to be a triangle, thus the name trigonal pyramid. If we were to add yet a fourth B atom to this, okay, so I remove this unshared pair here, and we drop in a fourth B atom. Now, we're going to have a tetrahedral configuration. So, when we're considering the electron pair geometry, when you have all single bonds, your electron pair geometry will always be tetrahedral. With a few exceptions, but I haven't shown them here. But for the most part, when you have all single bonds, you're going to have a tetrahedral configuration. And then if you have all four electron pairs occupied, well then, of course, the molecular shape will also then be tetrahedral. Now, what about bond angles? Well, when we consider the bond angles, when you're looking at all four of these, the bond angle here is going to be 109.5 degrees. Okay, so when all of them are occupied, it's going to be 109.5 degrees. However, when you have an unshared pair, so like on the trigonal pyramid, the bond angle won't stay at 109.5 because what happens is the unshared pair will repel more than the shared pairs. So take, for example, this molecule. The stick at the top here, this will represent an unshared pair. And the other three, of course, are bonded pairs. But what I'm getting at here is that this unshared pair that I'm holding onto is going to repel the other ones more than they will repel themselves. So these will kind of squeeze down like this. Now, this is, of course, an exaggeration. So now you can see the molecule is, the bond angles between them will be smaller or less than 109.5. Now, if I release it, you can kind of see how it would be 109.5 would look like that. So again, when that unshared pair is there, it will repel the others more so, and as a result, the bond angles will be less. So the bond angle for a trigonal pyramid will be less than 109.5 degrees. And for a bent configuration, then you'd have two unshared pairs that'll also be less than 109.5 degrees. When we consider, however, the linear molecule, you only have two atoms, so there really isn't a bond angle between two atoms. So it's just Na, not applicable. So that's when you have all single bonds. So now let's consider when you have one double bond. So if a molecule has just one double bond, and so if we look at substance atom A, and is double bonded to B, it will then have two pairs of electrons that will be unshared. And we would draw them off like this. Okay, so we have two unshared pairs attached to this. The electron pair geometry then would be a trigonal configuration. In other words, you have a set of electrons right here, these two pair, and then these other two. And as a result of these three sets of electrons, they'll repel each other in such a way that you will form a trigonal planar. So the electron pair geometry is trigonal, if I could spell, trigonal planar. The molecular shape, again, if you only have one B atom attached here, is going to be linear again, because when you only have two atoms, it's always going to be linear. But let's assume for a moment that we add a second B atom to this. If we add a second B atom, then we are going to remove one of these pairs of electrons and make it into a bond. And then it'll be off to the side like this, and it'll be a bent configuration. So at first, before when I showed you this one, here's when you have just one B atom that's double bonded to our central atom. And if we add a second B atom to this, now keep in mind, see that these electron pairs are all kind of falling into one plane. In other words, this pair, and the double bond back here is all falling into one plane. So now we add that second B atom to this, and we'll have, if we just look at the looking at the atoms alone, if you look at these three atoms alone, we can see it's a bent configuration here. But the electron pair geometry will continue to be a trigonal planar. In other words, if you look at the endpoints of the electron pairs, okay, consider the endpoints of the electron pairs that are shown here in this this molecule, then you would have a trigonal planar configuration. And if we add a third B atom to this, this will then form a trigonal planar configuration. So this is how it would look then if we were to add that third B atom. So it's going to be like this. And this molecule, of course, falls all in one plane. Again, trigonal planar. It forms a triangle, and the whole triangle lies in one plane. So I erase this pair of electrons here and put in our bond. Now this bond angle is easy. You can calculate this one much easier than the other one. The other one actually involves it can be calculated. 109.5 can be calculated, but it gets a little more complicated. The mathematics in it is a little more complicated. Here it's very easy, because we all know that a circle has 360 degrees all the way around. So if you have break that circle into three equal parts, well, then the bond angle here would simply be 120 degrees. So here we have 120 degrees for our bond angle. So for the trigonal planar, 120 degrees. And again, because with the bent configuration, we only have two B atoms attached to that central atom, then there's going to be an unshared pair. If there's an unshared pair, then that will cause the bond angle to be a little bit smaller. So this would be less than 120 degrees. And as before, when you only have two atoms, you don't have any bond angle at all. It's just not applicable here, just two atoms. So now let's consider when you have two double bonds or a triple bond. When you form two double bonds or one triple bond in a molecule, the molecular shape becomes very simple. When we form that second double bond, what it will do is it will force everything into a linear configuration. So, for example, if I had something like this would just be carbon dioxide. I'd have the oxygen here, carbon in the middle, and oxygen over here. Because of the two double bonds, it'll just force it into they're going to, again, those electron pairs are going to repel each other, and the furthest they can get from each other would be 180 degrees. So when we have, let's just consider again a double bond. Let's say A double bonded to B. Okay, it's going to be linear. And I'm sorry, with another B atom in there. Okay, so if you have that configuration, it's going to be linear. Again, these electron pairs are going to repel each other. Okay, so they're going to push away from each other so that we end up with 180 degrees here. That's as far away as possible they can get from each other. And so when we have the two B atoms attached to our central atom, it's going to be linear. The same is going to be true if we created a triple bond. If we create a triple bond in here, you're going to either have an unshared pair here, which is still going to be a linear configuration for electron pair geometry, okay? Or you could bond something to this. So there could be another element bonded to here. Could be the B atom again, or a different atom. And so we'd have another linear configuration for this. So this is with a double bond here. So if we have two B atoms, it'll also be linear if we have, oops, I should have put two double, or if we just have the one triple. Bottom line, when you have two double bonds or one triple bond, the molecule automatically falls into a linear configuration. And so the complexity of the molecules gets worse with single bonds. So going back to the original, when we just had all single bonds, this is going to occupy three-dimensional space. When we consider one double bond, this is now going to occupy two-dimensional space. And when we add that another double bond to that, so in other words, here we have just the one double bond, it draws in that one atom into the plane, so that causes it to become two-dimensional. If we create another double bond or form a triple bond, that'll draw it in so that it forms a one-dimensional object. So to summarize then, you really only have 5 different shapes that we have to worry about or can be concerned about in our tests. So you're going to either have tetrahedral, linear, bent, trigonal pyramid. Those are 4 of them. And then trigonal planar. That's the 5th. The others are all repeats. So all these need to be memorized. All the bond angles need to be memorized. And the shapes. And that's the summary of how bond type affects molecular shape.